Imagine crushing a mountain down to the size of a sugar cube, now make it spin hundreds of times per second. That's a pulsar. It's the dense, spinning core left behind after a massive star explodes. This tiny sphere, no wider than a city, packs more mass than our sun. A teaspoon of its material would outweigh a fleet of battleships. Atoms are crushed out of existence, leaving only neutrons packed impossibly tight. This is neutronium, a new state of matter, born from cosmic violence. When a giant star collapses, it spins up like an ice skater pulling in her arms, reaching dizzying speeds. Combined with a powerful magnetic field, this spin turns the pulsar into a cosmic generator. It shoots out beams of energy, sweeping across the galaxy like a searchlight. We only see a pulsar when its beam points at Earth, a brief, regular pulse of radiation. Each pulse is the heartbeat of a dead star, a rhythm echoing its violent birth. Pulsars are scattered across our galaxy, silent beacons in the dark. They push the limits of physics, where gravity and magnetism behave in ways we can barely imagine. These are nature's laboratories, testing the very edge of what's possible. Pulsars remind us that the universe is stranger and more wonderful than we can comprehend. They are cosmic tombstones, yet more alive than many stars. Their rapid pulses tell a story of extremes, density, speed, and the relentless power of gravity. Every pulsar starts as a massive star, far larger than our sun. For millions of years, it fuses hydrogen into helium, shining brilliantly. Deep inside, gravity and fusion battle for dominance. When the star runs out of hydrogen, it fuses heavier elements, layer by layer until it reaches iron. Fusing iron consumes energy, so the core's furnace shuts down. Gravity wins in an instant, the core collapses and the outer layers crash inward at incredible speeds. The result? A supernova, a titanic explosion that can outshine an entire galaxy. This explosion scatters heavy elements, gold, platinum, uranium, across space, seeding planets and life. At the heart of the blast, if the star was massive enough, the core survives as a neutron star. This remnant is a tiny, ultra-dense sphere with the mass of a sun. Sometimes this newborn neutron star spins rapidly and has a strong magnetic field. It becomes a pulsar. Pulsars are the cosmic relics of these stellar cataclysms. Their existence connects us to the life and death of stars. We are quite literally made of stardust from these explosions. The story of a pulsar is the story of transformation, star to supernova to spinning beacon. Each pulse is a reminder of the universe's cycle of creation and destruction. Pulsars are the ultimate legacy of stellar fire. Dive into the heart of a collapsed star and you find matter under unimaginable pressure. On Earth, atoms are mostly empty space, but in a neutron star, gravity crushes that space away. Electrons and protons merge, forming a sea of neutrons, hence, a neutron star. This sphere, just kilometers wide, holds the mass of our sun. A thimbleful would weigh hundreds of millions of tons. Neutrons are packed as tightly as physics allows, creating neutron-degenerate matter. The surface is smooth, mountains only millimeters high, and the core may be a superfluid, matter that flows without friction. Not every neutron star is a pulsar. It needs rapid rotation and a powerful magnetic field. As the star collapses, its spin and magnetic field intensify dramatically. The result, a spinning, magnetized object ready to become a pulsar. This is matter at the edge of possibility, a realm we can't replicate on Earth. Pulsars are the ultimate test of our understanding of physics. A pulsar is a tiny, dense star spinning at incredible speed, with a magnetic field billions of times stronger than Earth's. Its magnetic poles don't line up with its spin, creating dramatic effects. The magnetic field rips charged particles from the surface, accelerating them to near light speed. These particles shoot out as beams of radio waves, X-rays and gamma rays from the magnetic poles. The beams are always on, but we only see a pulse when one sweeps past Earth, like a lighthouse beam. The famous lighthouse analogy explains it. The light is constant, but we see flashes as the beam rotates. Our telescopes catch these pulses with clockwork regularity. Some pulsars spin so fast we see hundreds of pulses per second. The regularity of these pulses makes pulsars some of the most precise clocks in the universe. The lighthouse effect turned a cosmic mystery into a triumph of physics. Each pulse is a signal from the edge of what's possible. Pulsars are nature's ultimate beacons, sweeping their light across the cosmos. Pulsars spin at mind-boggling speeds. Some rotate over 700 times per second. Imagine a city-sized object, heavier than the sun, spinning faster than a blender. The surface moves at a fraction of light speed, held together by gravity billions of times stronger than Earth's. If you stood on a pulsar, you'd be crushed instantly. Gravity keeps the star intact, even as it spins at these extreme rates. Over time, pulsars slow down as their beams carry away energy. This gradual slowdown is measurable. Young pulsars lose a few microseconds of spin each year. The energy for the beams comes from the star's rotation. Eventually the pulsar slows too much to emit beams, becoming a quiet, dark neutron star. The cosmic lighthouse goes dark, but the dense remnant remains. Pulsars are spinning tops, winding down over millions of years. Their life as cosmic beacons is finite, but their legacy endures. Each spin is a countdown, marking the passage from brilliance to silence. Pulsars were discovered by accident in 1967, when Jocelyn Bell Burnell found a repeating radio signal. The pulse was so regular, it was first thought to be a sign of alien life. Soon, more signals were found, nature's clocks, ticking with astonishing precision. Pulsars became tools for science, allowing us to test Einstein's theory of general relativity. In 1974, a pulsar orbiting another neutron star provided the first indirect evidence for gravitational waves. By timing the pulses, astronomers confirmed Einstein's predictions and won a Nobel Prize. Pulsars let us study gravity in its most extreme form. Today, arrays of pulsars are used as galaxy-sized detectors for gravitational waves. These cosmic clocks help us listen for the faint echoes of the universe's most violent events. Pulsars are not just remnants, they are instruments for exploring the fabric of reality. Pulsars are precise, but sometimes they suddenly speed up, a glitch. This brief jump in rotation reveals the strange physics inside neutron stars. The leading theory, the superfluid core spins faster than the crust, building tension. When the tension snaps, the core transfers energy to the crust, causing a glitch. It's like a sudden coupling between a spinning soup and its bowl. Each glitch is a natural experiment, offering clues about matter under extreme conditions. Glitches show that pulsars are dynamic, not just ticking clocks. The energy release can twist the pulsar's magnetic field, changing the pulses we see. These events reveal a turbulent, chaotic inner world. Studying glitches helps us understand the layers and behavior of neutron stars. Pulsars are active, evolving objects, not static relics. Their steady heartbeat hides a stormy interior. Pulsars are among the most hostile places in the universe. Their beams of radiation would instantly destroy any life in their path. Planets near a pulsar are sterilized, their atmospheres stripped away by relentless energy. The area around a pulsar is a deadly bubble of high-energy plasma, a pulsar wind nebula. The Crab Nebula glows from particles accelerated by its central pulsar. Pulsars can only exist up to a certain mass, beyond that, gravity wins. If a neutron star gains too much mass, it collapses into a black hole. The pulsar's light vanishes, replaced by a region from which nothing can escape. This is gravity's ultimate victory, a transformation from beacon to darkness. Pulsars are beautiful, but their power is a force of destruction as well as creation. Pulsars are more than cosmic oddities, they're laboratories for extreme physics. They let us study matter denser than anything on Earth and test the limits of gravity and magnetism. Each pulse carries information about the star and the space it's traveled through. Glitches reveal the superfluid world beneath the crust. Binary pulsars test Einstein's theories in the strongest gravitational fields. Pulsars challenge our understanding and expand our view of the universe. The elements forged in their birth are the building blocks of planets and life. We are connected to these spinning remnants by a shared cosmic history. Pulsars are the universe's lighthouses, clocks, and laboratories, reminders of the order and beauty hidden in cosmic violence. Through them, we glimpse the fundamental forces that shape reality itself.